First off, abbreviations and what I'm talking about. In this case, we've got two events. I need to change this slide because I don't think Tyreke Evans plays for the Kings anymore. Let A equal the probability that Tyreke Evans makes a free throw in a game, and B equal the probability that DeMarcus Cousins makes a free throw in his game. And this is saying he only shoots one free throw, and DeMarcus only shoots one free throw. So the probability of event A, we will abbreviate or see it, or from here forth known as, when we say PA, we read that as the probability of event A happening, or PA is the probability that Tyreke Evans makes his only free throw. And something that you guys have seen before in a lot of other classes, I would imagine, not necessarily even high school. I know you guys have done it in, say, 2nd, 3rd, 4th, 5th grade. Is Venn diagrams, and that's kind of where we're going to get started here with probability. So the probability of event A, I'm just going to make a circle there, label it A, and Venn diagrams, if you'll recall, you kind of put the things inside that fit, and then we'll talk about overlapping in a second, but probability of event A, that would be everything inside that part of the circle. Again, that should be pretty much review information. The other thing that is probably new for all of us is probability of event not A. More specifically, how we write it. Not A is pretty easy. I think you guys are going to say, well, if I have a circle there, and that's A, I'm going to shade in the area that is not A. Everything that's not A is everything outside the circle. In the context of this problem, if event A is making this free throw, everything inside the circle is him making the free throw. Everything outside of the circle is him missing the free throw. Again, that should make sense. But what I want to kind of link here is the idea of what not A is. And it's written as probability of A with a little c. It looks like the c is an exponent. Okay? And, not A will be referred to in this class as A complement. Okay? A complement. Yo. Mm-hmm. I don't know that it fits in that context, maybe a little bit. Complements kind of go hand in hand, I guess that's the best way I can describe it. Here's kind of the universal truth that I want to make you guys see here. In talking about this idea of a free throw, making or missing, it should make sense to you that he's either going to make the free throw, which is event A, or he's going to miss the free throw, which is A complement. Okay? Now, probabilities are usually represented as decimals. I think you guys are okay with that. 0.5, 50%, 33%. You guys have seen decimals, it's percent. Probabilities, is that okay? You guys okay with that kind of link there? Okay. Then it should make sense to you if the probability that he makes a free throw is, say, 85%, then the probability that he misses a free throw is what? 15%? Again, I'll say it. If the probability that he makes a free throw is 85%, just making that up, then it should make sense to you that the probability that he misses a free throw or his complement will be 15%. How did I get that? How many people got 15% when I said it just now? Okay. How did we get that? Okay. So there's something that you guys did. You said it's out of 100%. So even though I haven't talked about it, you guys know that, hey, it should make sense to you that either happens in A or it doesn't happen in A. But together, if I was to add those two things together, that's all my probabilities, correct? All my probabilities should sum to what somebody already said, 100%. Or, since in this class in statistics, our probabilities will be displayed as decimals, we know that 0.85 means 85%. and 0.15 means 15%, all of our probabilities will sum to 1. Okay? And that should make sense. Or to write it generically, the probability of an event plus its complement will always sum to 1. And hopefully you understand that idea. Because later on, we will use this as, say, an algebra equation. We'll substitute in like A, we'll solve for a complement, or you're going to use and have to kind of work around that. Okay? All right, that's the terminology. I'm just going to draw some pictures now. Probability of both A and B. Probability of both A and B. We call this an intersection. If that's event A, that's Tyreek making his free throw. That's event B, that's DeMarcus Cousins making his free throw. The probability of A and B, you should be okay with it being, that's both Tyreek and DeMarcus making their free throws. And it should also make sense to you, it's the area that they overlap. Okay? The area they overlap. We will write that. It's called the intersection. And we will write it as probability of A and B. And you may have looked at this in your Algebra 2 class. I don't think you do it in pre-calc, and I'm positive you don't do it in calc. Anybody Algebra 2 this stuff? I don't remember if they did it in Algebra 2. How about classes before Algebra 2? You guys see this kind of stuff, Venn diagram stuff before? Ish? Venn diagrams? In English? All right, intersection. The easiest way for me to remember that vocabulary word of intersection, think of an intersection and a straight. It's where two things meet. It's where they overlap. Two things meet where they overlap. Okay, probability of either A or B. This is some weird wording for you guys. I know it is. I'm going to explain it. When it says either A or B, it actually means A or B or both A and B. Okay? In stats, if we see it say either A or B, it means it's okay if it's A. It means it's okay if it's B. It's okay if it's both A and B. And when that happens, we call that the union. And we write that as probability of A union B. Okay? I remember kind of the frown as the intersection, and that's hard to do. It's where two things meet. It's a rarer event. I remember a union is happy. It's everybody together, so it's everything in there. Okay? I just pretend that U is a smile. See, there's the two eyes. So U, union, happy, everybody together. Intersection, it's a rare event. It's where they touch. They have to have more things in common. Okay? Probability of only A. Probability of only A. Again, I forget what color I'm doing in. Okay. Tyreek is event A. DeMarcus is event B. Probability of only A. This is specific here. Hopefully, if you're thinking in terms of shading, you want to shade this only. Does that make sense? Now, the hard part. I want to write this in stats language. The probability, because I showed you what an intersection looks like, that's the probability of A and B. I showed you what a union looks like, which is the probability of A union B. And I showed you this new looking at with A complement, which is not A. So we're looking at the probability of only A. See if you can read my stat E's right now, and hopefully you'll agree with it. Okay? This is the hard part. You're going to be doing some stuff like this on your homework tonight. It's going to give you the stat E's, and it's going to say make a sketch. It's going to give you a sketch, and it's going to say write it in stat E's. Hopefully you're reading this bottom line that says the probability of A intersected, another name for intersection is and. So the probability of A and everything that is what?
Not B.
Not B. So if we think of everything that's not B, that's everything outside of my red circle. If I think of everything that's A, that's everything inside of my blue circle, including that part. That's A. If it's going to be an intersection of everything that is not B and A, then I don't get to have my middle part in there. And again, that should fit for you, the probability of A and not B. You should see how it's an intersection. Questions or clarifications on that? Okay. Probability of only B, if you guys figured out how not A works, then the not B or only B, you kind of realize it's going to look like that. And you're hopefully realizing probability of that is B and everything that is not A. Okay. By the way, it doesn't matter the order. This says the same thing as this. Okay? But realize that these two things say two different things. The right-hand side and the left-hand side of the board say two different things. All right? Probability of exactly 1. The probability of exactly 1. That means either Tyreek making his free throw or DeMarcus making his free throw. Exactly 1. Again, everything in his A is Tyreek making his. Everything in B is DeMarcus making his. Exactly 1. That means Tyreek can make it and DeMarcus can miss it, which hopefully you agree is that area there. The other thing that can happen, the other probability that can happen, is that Tyreek can miss and DeMarcus makes his. That's exactly 1 free throw being made. Tyreek makes it, DeMarcus misses, or Tyreek misses and DeMarcus makes it. So, this probability statement is a definitely tricky one. We agree that that's Tyreek making his and DeMarcus missing his. It's from the previous one. So we agree that this is DeMarcus making his and Tyreek missing his. So this is just one person making it, and this is just one person making it. The probability of exactly 1 will be a union, because union's everything. It's okay if it's the red shaded. It's also okay if it's the blue shaded. Union's all of it together, isn't it? So it's the union. It's Tyreek making it, DeMarcus missing it. Or, that's a union. Another way to see union is or DeMarcus making it and Tyreek missing it. Make sure you're becoming, what I want you to do is become fluent in this stat E's here and make the connection to A, the probability problem, and that Venn diagram. It's really vocab and seeing things together. I think this last box over here, neither, is one of the easier ones. I think exactly one is the hardest one to see in terms of studies. Is it okay if I erase that? All right then. I want you guys in your paper right now. I'm going to shade probability of neither. I want you to write my stat statement for that. Okay? Go ahead and write the studies for that. Studies, hopefully you got this. Probability of not A and the probability of not B. How many people got that one right? Good. Good. Another one. Vocab. Disjoint or mutually exclusive. Disjoint or mutually exclusive. You're going to want to write this definition down. There's a vocabulary word that's going to show up multiple times. Disjoint events have no intersection. Mutually exclusive means the same thing as disjoint. Mutually exclusive and disjoint mean the same. So an example of disjoint or mutually exclusive events would be people over the age of 80 in event A and people younger than 3 in event B. There's not a single individual that's going to be both over 80 and under age 3 at the same time. Okay? That makes sense? Disjoint, they're not connected, they're not going to touch. Mutually exclusive, the word exclusive means just with that and nothing else. So mutually exclusive means that's not, it's going to be just by itself, nothing else. Just by itself and nothing else. Exclusive, you're just by itself with nothing else. So I remember that. Generic rule. This is a rule on your formula sheet. You probably haven't seen it yet, but probability of A union B is going to equal the probability of A plus the probability of B minus the probability of A and B. Okay? You may or may not have used that before. It may be familiar to you. If not, it will be familiar to you. Like I said, we're going to use it multiple times in this class. In fact, we're going to use it right now to calculate some probabilities. Hopefully, you'll understand how the studies matches just to a generic problem. Today is the basics. I will tell you that probability problems we will get really difficult by the end of the week. Okay? So here's my advice on probability. I'm going to say it a couple times. When a probability problem is easy, and this one's going to be easy, when a probability problem is easy, keep it easy. When a probability problem is hard, keep it hard. Don't make the easy problems hard, and don't make the hard problems easy. Okay? Because that's what's going to happen. It's going to be the biggest thing with students in probability. They see a problem, and they want to think about everything underneath the sun they know about probability, and so they're going to apply a harder or more challenging formula to an easy probability problem. That's big error number one. The other error that I see is students say, here's this complex probability problem. Oh, this is an easy one. I'm just going to use a plug-and-chunk formula and get my answer. Okay? When they're easy, keep them easy. When they're hard, keep them hard, and don't confuse them. Let's assume Tyreek shoots 80%, the Marcus shoots 70%. The probability that they both make free throws is 65%. Find the probability that at least one free throw is made. Okay? Transferring this over into studies, and I will also make a Venn diagram out of that. Transferring this over into studies, find the probability that at least one free throw is made. If you've been tuning in with me, that should read to you as a union. Tyreek can make one, they both can make one, or just DeMarcus can make one. That's a union. So reading into studies, this asks for a union. We know the union, I just gave you that formula. The probability of A or B, union, is the probability of A plus the probability of B minus the probability of A and B. So for this part, that is a straight plug and chug formula. I'll do this on another page so I have a little bit more room.
Wait, it's at least one. Can both of them still make it?
What's that?
It says at least one. Both of them still make it?
Yes. But this should come out to be less than 1. And it will. And I'm going to make a kind of a picture of it so we can kind of see how things fit. All right. Probability of A union B is what we're looking for. Hopefully right now this is a straight plug and chug for you. Probability that Tyreek makes it is 0.8. The probability that DeMarcus makes it is 0.7. And the probability that they both make it is 0.65. So the probability that either Tyreek makes it, or they both make it, or DeMarcus makes it by himself is going to be that. That's calculator crunch, or you can do it in your head. I think it comes out to be 0.85. Is that right? Plus you guys can check me on that. Does that work? Good. A visual to go along with this. It sometimes helps. Plug in what you know. Well, here's the catch, and this sometimes confuses students. I'm going to make that a little bit bigger. The probability that they both make it is 65%, right there. Do we agree with that? That's both of them. Now, students want to plug in Tyreek's 80%. They want to plug in Tyreek's 80% right there. And I'll tell you right now, we've got a problem. If Tyreek's 80% is right there, and that's 65% right there, then Tyreek makes a free throw 0.8 plus 0.65. So Tyreek is making a free throw 1.45 or 145% of the time, which he can't do that. It is impossible. So my question really then becomes, what can I write in here? If they both make it 65% of the time, and Tyreek makes it 80% of the time, hopefully you'll agree with me that the event that just Tyreek makes it, which is this part right here, will be 0.8 minus 0.65. Because I don't know what that is. I can calculate that. I think it comes out to be, what, 0.15, 0.15? Okay. Now, does the whole red circle equal 80% of him making a free throw? Yeah. Does it still match with our 65% of them both making it? Yeah. And if you wanted to see DeMarcus, well, he's the blue circle. That's was what, 70% of the time? It stands to reason, hopefully, if they both make it 65% of the time, then he's only going to make it by himself 5% of the time. Okay, sometimes that Venn diagram helps. If the union is 85%, that's Tyreek making it, both of them, or just DeMarcus, it's 85%. What's the probability that they both missed a free throw? %? Well, if 85% is on the inside, because that's my union, it should make sense that 15% is on the outside because it's either on the inside or it's a complement on the outside. Okay, so does the Venn diagram match with kind of what we know? And can you see where I'm getting all these probabilities from? The rest of them, find the probability that neither free throw is made. We just talked about that. In SETIs, that's the probability of Tyreek missing and also DeMarcus missing. Probability of Tyreek and DeMarcus missing, according to this, is 0.15. And I can get that in terms of a complementary event. Does that make sense? Should. Find the probability that exactly one free throw is made. This is where this diagram comes in handy. Bless you. Exactly one free throw is made. That's Tyreek making his and DeMarcus missing. That's DeMarcus making his and Tyreek missing. Probability exactly one should be 0.2 there. 0.15 plus 0.05. Yeah, see how this probability stuff is almost just like mind games? It's really all it is. 0.15 plus 0.05 there. Oops. Oops. Okay. And again, you should have had the picture of that. We already drew a picture of that. You should see how the studies matches. And that's probability. That was the long one. That was right before I had you guys sketch it. On the probability that DeMarcus makes his and Tyreek misses, you probably already got that. You agree that that's going to be 0.05. Yeah? 0.05 there? Do we agree? Okay. All right, next up, we're looking at flipping a coin. The list of all possible outcomes, another vocabulary word for you. It's called sample space. Sample space is the possible outcomes. Consider the event a coin is flipped twice. Okay? Coins have what? Two sides. One of them's a head and the other one's a tail. All right, so we're flipping the coin. My sample space, that's all the possible outcomes. What is a possible outcome? Heads and heads. I can flip the coin and get a head, and flip the coin and get a head. What's that? Another outcome. I heard a heads and a tail, and I heard a tail and a tail, and then tail, and then a head. Those are my only four possible outcomes, aren't they? I don't know. Some of you can land it on its side exactly and have a miracle. Discounting the very rare probability of landing it on its side and sticking there, these are our four outcomes. Find the probability that at least one tail is tossed. At least one tail is tossed. Think back to your probability. Some of you guys are already thinking it's 75%. The real easy way to look at it, how many times does that event happen over the total amount of times? How many people realize that probability is really just what I call success over total? How many times does this thing you want to have happen divided by the total amount of things that happen? Right? And in fact, isn't your test score as a percentage on an exam success over total? For example, you got 19 points out of 25. That's 19 out of 25 correct. Isn't that percentage really your probability of what you got any given problem correct? Right? It's kind of the same thing. Probability success over total. You'll hear me say it over and over again. Think about it easy. Success over total. Success in this case is one tail. At least one tail. That means it's okay if I go tail. There is 1, 2, 3 successful situations out of a total of 4 successful situations. You guys already told me, Mr. Wood, that's 3/4 or 75%. We write it as 0.75 or 3/4. Find the probability that no tails are tossed. Well, duh. That's going to be 1 out of 4 or 0.25. I'd like to point out that these two events are complementary events. Either you toss a tail or you don't toss a tail. That makes sense? Just getting you guys on the same page vocab-wise. Once you see the process, you're like, the math is pretty easy, and indeed it is. All right? Two cars arrive at a stoplight. The probability that the first one stops is 60%. I probably should say stop sign. The probability the second one stops is 70%. The probability that they both stop is 40%. Okay? Find the probability of A union B. In fact, I'd like you guys to do this problem in your groups right now. I think you guys can do it. Okay? All right, checking your answers. Should have gotten 0.9 for the union. Only A. Should have been 0.2. Exactly 1. Exactly 1 should have been 0.5. Neither stop should have been 0.1. And the probability that B doesn't stop, should be 0.3. All right. The next up. Ooh. Wait. There. E 0.3. Probability that B doesn't stop. This here. Woo. That was pretty awesome. I did not know I could do that. This is the probability of B. Okay, which represents in the context of this problem the car B stopping. If it's asking for everything not B, it's everything outside of B. So if everything inside of B is 0.7, everything outside of B is 0.3. It's a complementary event. You can also see that as 0.2 plus 0.1. Okay. All right. Classical probability. We're still looking at that probability piece, as I told you before. We're going to get to tomorrow. This is what's called the law of large numbers. That's something you're going to need to know in just a second. What I've shown you here is a graph of somebody who has rolled a fair dice. That number is 2,000. Somebody has rolled a fair dice of 2,000. And what they did is they calculated the number of times that they rolled a 1. And they ran a probability for the whole thing. For example, they sat there and rolled the dice, and I really want to look at just the first 200 rolls. That's from 0, that's 200 there. I want to look at just that part of the graph.
It's crooked. Yeah, the low of that peak is 200.
The low of this what?
The peak that you put your line through.
My line's not straight?
No, not at all. It looks like you.
I'm always crooked.
Doesn't follow you.
So let's go like this, so you guys don't get cranky about straight lines.
Yeah.
Is that straight? It better be straight this time.
Yeah.
Ish. In probability, everything's ish. We're going to find that we're going to report things with 95% confidence and 99% confidence. We're always using ish. All right, I want to look at 0 to 200. This is me, or not me. This is somebody rolling a dice, and they're counting the probabilities. Hopefully, you'll agree that I roll the dice once. I'm either going to get a 1 or I'm not going to get a 1. So the first time I roll the dice, my probability is probably not going to be a 1. So do you agree that the probability of me rolling a 1 the first time is going to be 0 out of 1? Because I did not roll a 1. Success over total. Then I roll it again, it's going to be 0 out of 2. And then I might get a 1 there, and it's going to be 1 out of 3. So now my probability of rolling a 1 is 0.3333. I might get another 1, make it 2 out of 4. That'll bump it up to 50%. But then I'll probably not get a 1, and not get a 1, and not get a 1, and then get a 1, and then not get a 1. Do you agree that I can keep running and calculate this overall probability for the number of rolls of the dice? So what you have in the first 200 rolls is you see that variability or that fluctuation of ones. Again, I think you guys would agree with me here. If I gave you all a dice, I don't have time today, we'd actually do this. But if I told you guys all to roll the dice 10 times, and I said, I only want to know the number of times you rolled a 1 individually. And let's say there's 40 people in class, 40 people times 10 is 400 rolls of the dice. And then I asked us to add up all the ones total. Wouldn't that give us a probability for the whole 400 rolls of the dice? Okay. Here's what the law of large numbers says. 400 is a large number of trials. That probability would be really close to 1/6. Because I think you know, theoretically, me rolling a dice, the probability of me getting a 1 is 1 out of 6. You guys agree with that, right? That's kind of a known thing. But that doesn't mean, and this is where statistics come into play, it doesn't mean if I roll a dice 6 times, I'm guaranteed to get a 1. In fact, when you guys did your little experiment with 10 rolls of the dice, some of you would, quote, get lucky, and you might get 3 or 4 ones. Does that idea make sense? Well, there's other people in your group or other people in the class that would be quoted getting unlucky, where they might only roll 1 1. Do you see that the people that had 3 and 4 or 5 ones would average out with the people who got 0 or 1 run, so that overall, that probability would be 1/6. And that's what the law of large numbers says. When you replicate something a large number of times, the relative frequency, x out of 400, 0 out of 1. As you repeat something a large number of times, the relative frequency will get really close, in fact, infinitely close, to its theoretical probability. That's how casinos work. How lotteries work. You might get lucky, you might be the one person who gets lucky, but over time, we know that it's going to be close to 1/6. Okay? So, law of large numbers. What happens? Number of repetitions that you do something, the number of trials. As you increase that number, the relative frequency, that's the data from your experiment that you're gathering. You're sitting there rolling dice. That relative frequency will approach its theoretical probability. And the best way I can say it is, think about rolling a dice 6 times in a row. You are definitely not guaranteed to roll a 1 exactly 1 time out of 6 when you're rolling a dice. Some of you guys will roll 3 1s, some of you guys will roll no 1s, some of you guys will roll 1 or 2. Very rare is going to be the person that rolls the number 1 6 times in a row. Can it happen? Absolutely. Will it happen a run of 10 ones in a row if I roll the dice 20,000 times? Yeah, probably. But remember, I'm averaging out for the number of times that I rolled it. I didn't roll any ones for 10 or 20 times in a row. Okay? So, law of large numbers there. The relative frequency of your event when you're doing that experiment, as the number of repetitions increase, you will get very close to the theoretical probability. We're actually going to use the law of large numbers to do some things that are called simulations in class, which is showing up more and more frequently on that AP exam. So simulations is definitely something the world of statistics is leaning towards, and it's also something that is happening in the real world in terms of what's called predictive modeling. Has anybody heard about predictive modeling? Okay. You may have heard it in terms of stock markets and housing markets. How many people have heard of people trying to predict the stock market, people predicting the housing market? You may have parents or family members that are in the stock market or are in the housing market. But really what they're trying to do is look at data and predict what's going to happen in the future based on that data. And it really ties around to that idea of simulation. And there's a really cool analysis that I'll get to when we get to that part of simulation is the Boston Celtics. So remind me to talk about the Boston Celtics when we get there. All right. We don't have time for the quick trial today because we are under the gun. I think I'll leave it for here. What time do we get out? 25? 25? Yeah, I think I'll leave it here. We'll end here.